I am Giora. I'm a data scientist at VFunction. It's a startup. And I'm going to be talking today about why and how I dare use deep learning in the context of statistical inference. I'm going to play a bit at first with a gray data set from OkCupid. It's about 60,000 OkCupid users who answered some demographic questions. So often at times, as a data scientist, you would ask yourself a very basic question: is there a relation between one variable and another? Here I'm asking, it's a silly question, but I'm asking it. Is there a relation between a person's age and a person's height? And it's a very simple question. You can plot, the data with a simple scatter plot. To me, this plot is intuitive. I say that for, say, adult women, I think there is no relation. And even the statistical test to answer the question, is it significant or not, are you right or not, is pretty simple. It looks like a linear relationship. You would probably compute a Pearson's R coefficient, okay, for linear correlation. Here it's in absolute zero. Of course, it's not significant, and the answer is intuitive. A different question might be a relation between two categorical variables. Is there a relation between ethnicity, being white or Asian, and reported drug abuse? Here it's categorical, like never, sometimes. Some of you might go for percentage tables, saying for each ethnicity, what is the percentage of people who answered never, sometimes, often, and some would use a mosaic plot. Okay, on the x-axis is the ethnicity, on the y-axis is the drug abuse reported, okay? And here, without knowing how many people answered the survey, it's a bit more difficult to know whether what I'm saying is significant or not. I'm telling you that it's 60,000 responded, so it's pretty significant. If you want to do the statistical test, you would probably use a chi-square test or report the results with a Cromer's V correlation. Cromer's V is is a correlation coefficient between 0 and 1, where 0 is no relation and 1 is perfect dependency, and it's very significant. Here you can see that, for example, Asian respondents are tend to statistically use drugs less, okay? And sometimes the relation would be between a categorical variable and a continuous variable. Like here, I'm asking whether there is a relation between sexual orientation and height. And here, specifically sexual orientation, say it's between straight and gay respondents. Obviously, when it comes to height, you need to plot men and women on separate plots. If you look at the left plot, it's swarm plot, okay? Another plot. I don't think, to me, there is a relation in either of the plots, but it turns out when you look at the numbers that straight men, on average, report that they are 1 centimeter higher than gay men. And surprisingly enough, if you do a t-test, okay, we had a Pearson R correlation, we had a chi-square test, here it's a t-test, then it's very significant with these many respondents. I don't know if it reflects any truth. It also could reflect the fact that straight men tend to exaggerate when it comes to reporting their height. I don't know. Okay? But so far we had pretty simple questions and plots. What if I ask if there is a relation between height and income? Okay, so again, two continuous variables and we do a scatter plot. But here the scatter plot is less obvious. Okay, it's less obvious what to answer to this question. On the left, you see men. On the right, you see women. And the income is at log scale. So when it comes to men, to me, it doesn't seem like there is a relation. But when it comes to women, maybe there is a relation. And if I ask what is the relation, you know, to model the relation, that's a whole different question. And I'm not sure how to do this in this specific scenario. So usually life is more complicated. Real data looks more like this, not like what I've shown you before. And many questions arise, especially when you're a beginner practitioner. Like, should I use the correlation coefficient? Is that okay? So I'm hoping that before that you would ask, is the pattern even linear? With women, it definitely wasn't. Oh, I heard there was a Spearman correlation coefficient in Statistics 101, and it's aparametric, so I can probably use that whenever, right? Can I use that here? Can I use this number and put it in my article? Should I use the log transformation for income? Is that okay? Many questions arise. If you're good at what you're doing, I hope that at least if you use a linear model, you would then perform some kind of diagnostics and like look at a residual plot and say, okay, is my residual plot okay? Ask a statistician, I don't know. Or sometimes people would approach me and because I'm in my education, I'm a statistician, and say, it doesn't seem to me like there is a relation. Can I just write that? You know, everyone can look at it and reach the same conclusion. Okay? So visual inference is an approach which is fairly new. It's about 10 years old, and it aims to eliminate all this, you know, all these questions about what I should do. The key to understanding visual inference is that we treat the plot as a statistics. The same way that a mean of a vector is a statistic of the vector of the data, the plot is also a statistics. And as a statistic, it's a function of the data from whatever space your data lives in into a 2D canvas. And as a statistics, you can gather more of it. You can permute your data, right? You can jumble up one of the columns of your data, get a slightly different data, and get another plot. And do it again, and get another plot. And do it again, and get another plot, okay? And you can judge your plot, your original plot, versus a distribution of these permuted plots, okay? And you can do it to every plot. A swarm plot, a mosaic plot, a scatter plot, okay? Under the null hypothesis, if there is no signal in your plot, in your data, they should all look the same. You shouldn't be able to discriminate your original plot from this set of plots, okay? Or if I say, ask 10 people, ask you guys, I shouldn't be able to get one specific obvious answer. It is assumption-free, it is parameter-free, and the question is how to present this set of plot. Right now, the most common way to do that is with what we call a lineup protocol. So here I'm asking whether there's a relation between a car's engine displacement and its horsepower. One of these plots is the original plot. The other 19 are permuted plot, where I jumbled up the data and replotted it. And I'm asking you, which plot do you think is doesn't belong here? Which plot is the most unique? Which plot has the most clear signal?
16, 11, 5.
I'm hearing all kinds of answers. I'm hearing 5 and I'm hearing 11. 16? Okay, so let's wait for the answer. Here I'm asking whether there's a relation between a person's gender and the answer to the question, is it rude to bring a baby on plane? It's a real survey, okay? So here we have female and male, and the answer is no, somewhat, and yes. Which plot is the most extreme plot, do you think? 18. Okay, here I only heard 18, maybe someone... What? Sorry, I didn't hear. And here we ask, is the relation between an actor's gender and the number of roles since his or her character ended. We have here 129 actors in US shows which were nominated for a Primetime Emmy, US drama shows, and the number of roles an actor had after his or her character ended is between 4 and 15 years after that. And again, I'm asking, which plot is the most extreme? 19. Anyone else? 0. What pops to my mind is that I'm hearing on less answers because it's hard to get the answer. And here, if I'm not mistaken, the original plot was 5. So I would say that according to this test, there is no difference between women and men. And in fact, if you perform the statistical test, any statistical test, I performed several because you can perform several statistical tests here, that's the answer you're going to get. There was no difference, okay? And this is a good example where the statistical test isn't that obvious, but we've seen that you can do it on any type of plot, okay? So this lineup protocol, some would say it democratizes statistical inference because it has been shown that kids can do it naturally. Everyone can do it. You don't have to prove to me that a t-test is a uniformly most powerful test to do this. You don't seem to get better at it over time. Most people are just good at it, but it takes you less time. There are all kinds of studies that have been done on it. And most research is on scatter plots. And there's a lot of usage in Amazon Turk because usually you would want a p-value and you would ask, say, n people what they think, and you, under the null hypothesis, it's a binomial distribution if people choose the specific original plot. Okay, so wait, where does that deep learning come into this play? So judging a plot, to me, immediately pops up as classifying an image, right? It's a classification task. And some data scientists, many statisticians have a slight aversion to deep learning and, shoving it wherever you want. But I claim it's very good for computer vision. And here the idea is to take a neural network and give it thousands of such plots. For a scatter plot, for example, you could sample from a bivariate normal distributions, thousands, tens of thousands, hundreds of thousands plots, and for each plot, let it predict whether it's significant or not, what is the correlation. If you're giving it many mosaic plots, like I have, ask it to predict the Cramer's V, or a swarm plus, ask it to predict the t-statistic, or again, whether it's just statistically significant or not. Training to predict the correlation, and it's very important this difference, not calculate the correlation, predict it, and if it's good, show it the lineup, and if it chooses the original plot, then yes, it's significant, okay? Okay, so I've used a really basic architecture of a convolutional network. Basically, you see this plot, it becomes my image, my data metrics, and it goes through the network, and at the end, I'm expecting an answer. In this case, I'm expecting linear correlation, like 0.73, okay? Nothing really fancy, and it turns out that it's kind of good. Here you can see the result on a test set with where I've sampled tens of thousands from sample size 50 from, say, a bivariate normal distribution, and we see that the network predicts our correlation pretty good. Here is when I sampled tens of thousands of bi-categorical distributions, where you can see that the network predicts the Cromer's V pretty well. And it is able to pick the original plot. So I owe you the answer. Here, everyone says 18, and it's indeed 18. Here it was 11. And up until now, you might be wondering, so what? I mean, convolutional networks can drive a car. So obviously, they can, approximate the formula for linear correlation. It's not a very difficult formula to approximate. But things do get interesting, and interestingly, they get interesting when I start looking at the computer's errors, where it was wrong, and I wonder whether it was really wrong. This is the computer's largest error, okay? The actual correlation here, if you compute it, is 0.46, but the computer thought the correlation was 0.1, okay? To me, I tend to agree more with the computer because this is, I think, a classic case of an outlier, and a statistician might use something called Cook's distance or whichever strategy you want to verify that these two observations are actual outliers. And indeed, when you just take one of them, the correlation drops to 0.08. So some would say that the computer was wrong, but some would say it was actually pretty robust to outliers. And when you look at this as a general pattern, which is what the computer learned, you want to see the general pattern. You don't want to see two specific observations which make your correlation higher than it should be. Okay, but things do get wrong, and obviously deep learning has its limitations. I can give you a few examples. Here I asked the computer whether there was a relation between a car's engine displacement, and this time it's fuel economy. So on the x-axis is displacement, and the y-axis is miles per gallon. What do you think is the most extreme plot? 9, right? It's easy for us, but the computer, after all that, chose 0. Why is that? Because the computer never saw a nonlinear relation. Okay, while we see all kinds of patterns, and we don't have to be trained on tens of thousands of plots. Okay. Here, the actual correlation is 0.64, but the network predicted 0.2. And this is why the network predicted 0.2, because it was always shown in a sample size of 50. It was never shown a sample size of 10. It doesn't know what to do with it. And even though this is a very impressive result if you're a social scientist, the computer was unimpressed. Also, you can input to a deep learning network whatever you want, okay? We know this is a trick question, and Cartman isn't really a plot, but the network predicted that it has correlation of minus 43.99, which is kept at -1. So the network thinks that Cartman is negatively, perfectly uncorrelated, okay? But it just goes to show how better we are as human judges, perceivers at these things than computer. But I'm not sure it's always going to be like that, okay? And whenever you shove in deep learning to the play, you have to ask yourself, does it have any value? So if I count the number of plots I have ever looked at, and I'm a statistician, say if I'm really optimistic, like 3 a day, 5 days a week, 52 weeks a year, 9 years since I graduated, maybe I get to 7,000. But my laptop can look at 20,000 scatter plots in 1 minute. My laptop can look at every scatter plot which was ever printed in every statistical textbook, every scatterplot that Ronald Fisher ever looked at, and every scatterplot that Carl Pearson ever looked at, in the course of 1 minute. Is my laptop a better statistician than me? I would say no. I think I just proved that. But could it be a better statistician than me? Maybe. I didn't even write that here because I didn't want to be that guy that would automate statistics. But you know, this is where it is going to, especially when it comes to diagnostics and looking at residual plots, which is a tedious work. And as any student of Statistics 101 would tell, you don't really know what to do with these residual plots, and are they okay or not okay. Okay, so I'm not going to be that guy who works on this project, but I promise you that somewhere someone is doing that, and I'm not sure that it's not an okay thing to do. Okay, there are many automated platforms these days which don't do any form of diagnostics. Maybe they should be, you know, improved by doing that, and not just doing automatic t-tests. And this is one way they can do that. So thank you. These are my references, and if you have any questions, I will answer them now. Now, right?
Yes. Brief summary. If you can give us a brief summary, and what are you going to do with this information tomorrow morning? The practical.
Well, I don't think you can do anything that's of use with this information tomorrow morning, but I think it shows you how statistics can be automated in a way that would save a lot of statisticians a lot of time in the future, and in a good way, you know, not just, you know, streaming data into an automatic t-test and just getting the result, but actually doing diagnostics, real diagnostics on real diagnostics plot. That's one example. Yeah.
So I was wondering, when you input plots into your model, did you look at, say, like how the results would be affected by things like, let's say, like the width of the points, or like if you plot with opacity or not, which sometimes is arbitrary and sometimes might actually give more information if you have like a whole body.
No. The short answer is no. I only did it for tens of thousands of scatter plots by sampling a bivariate normal distribution, and for tens of thousands of mosaic plots by sampling tens of thousands of bicategorical distribution. And then later I made all these adversary examples that you've just seen. But opacity is a great way to affect the model, and yeah, that's a great addition to this. Okay, thank you.